doing here. I don't think we filled in this last part. As the depth increases, the pressure increases. What if you took a bottle that was filled with water? Remember that video with the, was it Counting Crows? Is that Counting Crows? Yeah, I don't know Counting Crows. Well, what if you took a bottle that was filled with water and went 70, 80 feet underneath it? What would happen? Huh?
It would crush. It would flatten.
If it had air in it, sure. But what if it had water?
It would stay the same.
It would stay the same. The reason is that water, or all liquids, are what? Incompressible. But gases are compressible. You can take a gas and you can compress it down to a smaller space. So the bottle that they used in that video, it had something in it. It was just a gas. And gases are compressible. Right, so as the depth increases, the pressure increases, and we see that here in this formula. Here on out, oh shoot. You could have used the formula sheet. I'm sorry. You didn't really need the formula sheet, did you? Yeah, I'm sorry. You should have asked. I'm sorry that I didn't give it to you. But in the future, you have formula sheet for every quiz. And you'll have that for the exam, too. So this is on the formula sheet. As the depth goes up, the pressure increases. It's a direct relationship. If one goes up, the other goes up, as opposed to an inverse relationship. It's also a linear relationship as opposed to a quadratic relationship. So if this increases by, say, a factor of 2, this is also going to increase by a factor of 2. Whatever amount this increases, whatever factor it increases by, whatever amount you multiply it by, then this will also multiply by the same amount. Okay? As opposed to a quadratic relationship, which is where you have a squared number, right? Or some power. All right. So atmospheric pressure is really big. In fact, atmospheric pressure is 100,000 pascals. One atmosphere, which is a measure of pressure, is equal to 100,000 pascals. And remember a Pascal, we defined this early on, a Pascal is equal to 1 Newton per square meter. So it is the SI unit for pressure, 1 Newton per square meter. So when you're sitting right where you are, there are 100,000 newtons per square meter acting on your body. Like this is about, this little desktop area is about a square meter. It's a little less than a square meter. But that means that there, on this 1 square meter of material, there are 100,000 newtons of force. Remember, a person is, around 1,000 newtons. So that's like 100 people sitting on top of this. So if I put 100 people on top of this thing, what do you think would happen? I mean, just with one person, it sort of buckles a little bit. What would happen if I put 100 people on top of this shelf? The whole thing's going to break. So why is it that I have 100,000 newtons of fluid sitting on top of this thing, pushing down onto the tabletop? Why doesn't it break?
Because it's also pushing from the bottom.
Right. So the net force on it is 0. I have 100,000 newtons pressing down on this 1 square meter, and then I also have 100,000 newtons pressing up on that 1 square meter. So that's also why we don't feel that pressure. One, we're mostly liquid, right? So we're incompressible mostly. Mostly you're incompressible. Parts of you have gases in them. But then also that I have all these forces acting on me, but they're acting equal and opposite. And so we don't really feel that pressure as it's acting upon us. Sometimes we can experience it. Let me show you. This is I tried doing this experiment, and you can certainly try it at home, but it's a little tricky to get just right. And so I usually just sort of walked away looking like a fool. But this little kid does it pretty well, so let's just watch the video. Oh, he's a kid. I think that it was really his mother that did it for him.
At least she hopes so.
I've done it before. It's just a little tricky. You have to get your paper just right. Let's see. 7, I think? No. is it.
Crazy. And their weird elevator music.
All right. So, so the newspaper, like I said, the newspaper is here, and we have this column of fluid, this column of gas that's pushing down on it. And if I have a 1 meter by 1 meter, then the force that's acting here is equal to 100,000 newtons. You understand the difference? That it's the pressure is at 1 atmosphere, 100,000 newtons per square meter. But the force, when I have a 1 square meter area, is 100,000 newtons. So we also see atmospheric pressure at work in a barometer. Actually, let me show you the straw first. You ever used a straw? You know how straws work? This is a straw. What do you mean, no plastic straws?
They're illegal.
Where?
It's like the thing now.
Where?
Save the planet.
Oh, we're in Louisiana. So I have a straw, and I want to consume the water. Watch. Atmospheric pressure at work.
What's that atmospheric pressure?
Huh?
It's you drinking.
No, it's not me. I'm doing a very, very small amount. All I'm doing is making a slightly negative pressure inside of my mouth, but it's really the atmospheric pressure that's coming down and pushing on top of the water in the glass, and then it pushes it up into the straw and into my mouth. I'm doing very little. I just make a very slight difference between atmospheric pressure and the pressure inside of my mouth.
All you do is make a vacuum in the straw and the atmosphere does the
I
rest.
can't make a vacuum. Like, it's very difficult to make a vacuum.
Yeah, you need like a whole machine for it. Or
Well, that's why you
You're right. I make a slightly negative, like a slightly less
You
pressure.
decrease the pressure and then the pressure equalizes because in accordance to the atmosphere.
Mhm. So listen, if atmospheric pressure is what's pushing this down, then there must be a limit for the length of the straw. Because atmospheric pressure can only push water up so high. Okay? And so there is, it turns out, to be a limit to the atmospheric pressure, or a limit to the length of the straw. And I have another video I want to show you. You want to watch another video? We're not going to watch the whole thing. It's about 7 minutes long. But I just want to show you, this is a Veritasium video where they look at the world's longest straw, and they try to, it turns out the world's longest straw is 10 meters long, and that you can't have a straw that's longer than 10 meters because atmospheric pressure is only a certain amount. And it's the atmospheric pressure that pushes the liquid up into the straw. In order to have a longer straw, you'd have to have a higher atmospheric pressure.
Does that length vary according to how wide the straw is?
It doesn't vary according to how wide the straw is.
So if it's 10 meters, but like if
10 meters, right. And it goes back to this equation that we wrote last time, that the pressure is equal to rho times G times H. It's only the height of the straw that's important as it relates to the pressure. You see nothing here as it relates to the diameter or the cross-sectional area of the straw.
what's wrong?
Rho is the density. We'll talk about that in a bit. 10 meter straw, which is the limit of what you can have for a straw. So let's think about this, how this goes about. When you have a straw, say if you have a glass like this, and you have a straw that's there, what happens is you have this pressure that pushes down, that's the atmospheric pressure, and it causes the liquid that's in here to go up into the straw and then into your mouth. Now you create a slightly smaller pressure than the pressure that's 1 atmosphere outside of you. Who had a question? Yeah, listen. Okay, wait a second. You create a slightly smaller pressure inside of your mouth, and that causes a pressure differential. Remember that what's required to cause fluids to move is a difference in pressure. That came up in your reading, I think it was on your quiz too. That you require a difference in pressure in order to make fluids move. And that's what happens here. You create a difference between atmospheric pressure and the pressure that's in your mouth.
So, have you ever like sucked some water up into a straw or something? You put your finger over
Mhm.
it, it stays in there. Is that what this
Yeah, that's exactly. So that's exactly the same idea. That's a good illustration. Let me draw a picture of that. So if I have a straw, it's like a blown up version of the straw, and you put your finger over the top, blocking the top of the straw, you can collect water inside of the straw. Like whenever we go out to the fast food restaurants to eat, what we like to do is make snakes. You ever do that? You do that? Yeah, so you take the paper and you crump it up on the straw, and then you take it off, so you have that little straw paper all crumped up, and you put it on the table, and you put your straw in some water, and you do just like this, and then drop it on the paper, and the paper all wiggles like a snake. You ever done that? Just see me and Shelby. That's it. Y'all should try it. It's very interesting, right? Anything? Makes me want to go do it right now. What is it?
Pertaining to the previous formula, just like that sense. So this is pertaining to water, really. That the height that the maximum height is 10 meters for a straw.
Yeah, we're gonna get to that.
But if you have another substance with lower density, then it could have a longer straw.
Right.
And if it has more density, then smaller.
Mm-hmm.
Okay.
Yeah, let me come back to that because it's an important idea.
So would they use like colored water?
Yeah.
They could use
Mm-hmm.
that.
I think that should be like a. I mean, I'm not suggesting that y'all play like drinking games, but like I know that they say that students in college do that. I'm not sure that they do really. Like most of y'all just study or work, but that would be a good drinking game to see how long of a straw you could drink through, like a 5-meter straw. And the advantage of that drinking game is that you don't drink as much, and then you don't have to go to the bathroom as much.
And you know the answer, so you can bet your friends and make money.
Right. Uh-huh.
Yeah.
They think it's going to be easy, but it's not easy at all. So anyway, so with the straw where you hold your finger over it, you get 1 atmosphere of pressure pushing up in this part, and in here you get something less than 1 atmosphere, maybe 0.99 atmospheres, just something less. And so I get a smaller force pushing up here, and that allows the fluid to stay up inside of the straw. Try that. Do a snake next time you go to Haynes or wherever.
I actually had to explain it to somebody once because we went to eat at a restaurant and we ordered a Corona Rita.
Uh-huh.
It has like an upside down bottle of Corona inside of it, and she could not for life or understand
why.
why it was staying
Mm-hmm.
inside.
So that's how a straw works. A barometer. So you've heard of barometers before. That's what we use to measure atmospheric pressure. And this gets back to Stephen's question. A barometer looks like this. It is a dish that's filled with some fluid. Usually it's filled with mercury. And the barometer has a column that's turned upside down, kind of like in the Corona Rita, as you say, whatever that is.
It's a margarita with
Yeah, I know what it is. And then when you have the atmospheric pressure pushing down on the outside of this fluid, just like the straw, it pushes that fluid just here up into the column. And then you measure this distance. We'll call that H. Remember, pressure is equal to rho times G times H. So the height of that column is proportional to the pressure. Now, if that were water, what would the height of the column be? I also say that you have a perfect vacuum. So up here, inside of this column right here, you have a perfect vacuum. That means that the pressure is equal to 0. So if you could have a perfect vacuum in this column, how high would the column of water be?
That's limited. It's a little something over 10 meters.
Yeah, the limit is actually 10.1 meters, but yeah, it'd be 10 meters. So if it were water, it would be 10 meters high. And in fact, that was the first barometer. Torricelli, I think was his name, back in the 1800s, made the first barometer, and he didn't use water, he used wine. And he had to use a column that was about 10 meters tall. That's a tall column, 30 feet tall. And it's just very difficult to establish a vacuum in a column that tall with such a high column of water. So instead of using water, what could we use? We could use a substance that is what?
Denser.
if we use a substance that is denser, if we increase rho, that means that H will decrease for a given pressure. If we increase rho, which is what we do by using mercury, which is a very high density, if we increase this, that means that H will decrease. So instead of having a column that's 10 meters tall, we get a column at 1 atmosphere that's 760 millimeters. Okay?
So how do they get the drinks in there? Do they just flip it real quick?
I don't know how they do that. I've never made such a shot. Yeah, that's what they do. They just flip it upside down really quickly. And then the pressure keeps it up there. All right? So, what was I going to say? Oh, you've probably heard that number before, because that is atmospheric pressure. You all heard 760 millimeters of mercury?
No.
That's the atmospheric pressure. I said it earlier in the chapter, but when they report atmospheric pressure, they often report it in millimeters of mercury. In a similar way, you ever had, gosh, they don't use these anymore, but in hospitals they used to have blood pressure cuffs that you could see like a little column of mercury on the wall. You ever seen those at the doctor's office?
Yeah, they still got those.
They still got those? That's what that's measuring. It's measuring a pressure in exactly the same way here. By measuring the height of the column, that's how we measure the pressure that it's observing. You know, it's a little more complicated because you're comparing the pressure in the cuff to the pressure of the fluid in your arm, and we'll talk a little bit about that later. But it's still the same concept. The height of that column gives you the pressure, it's proportional to the pressure. By that P is equal to rho times G times H. All right, let's try these clicker questions. Okay, good. Just use it for now. We'll talk later. We can get it registered. So make sure you use it. It will go to your name when I register it to your name. We're doing the one on the left here. You weigh 180 and you stand on one leg. What's the pressure on your knee joint? No, not online. In class, we did the little clicker registration. I think you're already registered. Yeah.
She said I can start registering.
If you don't, it's not a big deal. Just keep using your clicker. All right, just a few more seconds. 1:10, I'll stop. Just guess if you're not sure. Okay, so remember, pressure is force over area. If I weigh 180 pounds and I stand on one leg like this, all of that 180 pounds is driven down through that one leg. If I'm on two legs, I only get 90 pounds per leg. Right? It splits it up. But here I'm standing on one leg, so I get a full force of 180 pounds on my knee, and I have an area of 0.5 square inches. And so 180 divided by 0.5 is 360. That's B. Okay. Why did y'all put C? No, D?
It's only because I didn't use a calculator. Yeah.
Oh, I see, yeah. You were thinking a half of 180.
Yeah.
But when you divide 180 by half, and remember, you won't be able to use a calculator on the test. This is equal to 180 times 2. What's equal? 180 and 360 and 9?
Like, you know, the pressure, like, one forecast is the same as the other one. 180 pounds with the knee would have to be the same as the leg. To balance.
Oh, but I'm not looking for the force. I'm looking for the pressure. And the pressure and the force are something different. So it is true that I'm 180 pounds on my knee, but it's true that I'm 180 pounds of force acting on my knee, but because my knee is only about a ½ inch square, that's 360 pounds per square inch. All right? All right, let's try this one on the right. How do we define pressure? I think, was this on the quiz? Yeah. So you have the answer. All right, just a few more seconds. We'll stop at 18. 18. All right, B is the right answer. Force per area. Oh, goodness. I'll tell you the one about Santa's helpers. Oh, what do you call Santa's helpers? Subordinate clauses. All right. All right, so you get it? Yeah. Yeah. So Pascal's principle. You'll need to know all these various principles, huh? No, I've never run out of jokes. Don't you worry about it.
It's pretty funny.
Mm-hmm.
I'm not worried.
Don't worry. We won't run out. You can't answer too many questions right.
So you got the answer.
Pascal's principle says when pressure is applied, to a fluid, in a closed container, that pressure is felt throughout the container. Look, let's say that I have a container, and I have a piston in it, and I can push down on the piston with a certain pressure. So I push down with a certain force, it has a certain area, and so I get a pressure that's force over area. Whatever pressure that I push on that container, that pressure is felt all the way throughout the container. I feel the same pressure all the way throughout. And the same here, that if I push here with a certain pressure, that same pressure is felt over here, over here. In fact, you can see, like, if I push down here, that the container becomes firmer up here as it goes if I don't push very small. That's Pascal's principle, that I can transfer pressure by pushing down here, and the pressure is felt up here. And that might seem really simple to you, and it is sort of simple, that I can transfer this pressure. But it makes very useful principle in a number of different ways. Like the heart applies pressure. Fortunately, when our heart pumps, boom, 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 it applies pressure that's felt throughout the body. That's how we're alive. A baby pushes on its mother's bladder, and that causes a pressure, right? When a baby, I don't know where your bladder is, but when a baby kicks on the mother's bladder, it increases the pressure inside the bladder, and then that makes it need to go, you know.
All the time.
Right, so it also comes up in hydraulic lifts. Every kind of hydraulic lift. You can just sort of use the bottom of the page there. In a hydraulic lift, it works like this. You have a system that's set up like this. A closed system. You have one piston over here and another piston over here. And so you push down with a force, and you have an area. I'll call this A1, F1. And then over here, I have a different area. A2. And have a different force, F2. The hydraulic systems are pretty common. If you go to the barber shop and they lift the chair up, you ever done that to you? That's a hydraulic lift. If you go to a tire shop and they lift your car up, they almost always use some sort of hydraulic lift. And what it allows you to do is to put in a small force and get out a big force. And it works like this. I know from Pascal's principle that the pressure, P1, whatever pressure I apply with that first force is going to be felt all the way throughout. So if I apply a pressure over here, P1, then I'm going to have that same pressure over here, P2. Okay? Now, that means F1 over A1 is equal to F2 over A2. What does that tell you, just from this figure, about the relative sizes of F1 and F2? Which one is bigger, F1 or F2? Down here in F1, F2, and they're equal.
Well, F2 and A2 would both be equal because it's division, therefore both numbers have
Let's
to
put
be
some numbers
bigger.
in.
It says that they're equal.
But that's divided by area that makes it equal.
Let's put some numbers in, and I think that might help you to see it. Let's say that A1 is 1 square meter. That's a big piston, but the numbers work out easily. And let's say that A2 is 100 square meters. And so what I have is, I have F1 over 1 square meter is equal to F2 over 100 square meters. And so let's say that F1 is, I don't know, 100 newtons. So I have 100 newtons over 1 square meter is equal to F2 over 100 square meters. So what would F2 have to be? Is F2 going to be bigger or smaller than 100 newtons in order to make this side of the equation equal to this side? A lot, no, not 100. It's going to be bigger. In fact, it's going to be 10,000. It's going to be 100 times 100. So F2 is going to equal to 10,000 newtons. I put in 100 newtons, and like Annette said, I get out a much bigger force. The pressures are equal, but the forces are not. Let me write it a different way, okay, mathematically. So if I take this, I can say that F1 is equal to A1, or excuse me, yeah, A1 over A2 times F2. All I did is I just solved for F1. Really what I did is I multiplied both sides of this equation by A1. In order to get rid of the A1 on this side, I multiplied this side by A1 and that side, and I get this. So what that means is that F1 is the ratio of the areas times F2. Or F1 is 1 over 100 times F2.
You're talking about to figure out what you just did?
Yeah, the hydraulic lift. So you put in a small force in the small piston, and you get out a big force in the big piston. Small force in the small piston, big force in the big piston. And that's Pascal's principle. It just says that the pressures are equal. We'll do a sample problem soon. Yeah. So remember, we're going through the there are 3 or 4 different types of pressure. The pressure due to the height of a column of liquid or fluid, that's the atmospheric pressure. Then there's the pressure due to an external force, and then we'll also see the pressure due to the interaction of molecules and pressure in solids. Now regarding pressures due to an external force, there are 3 different types of pressures that you measure Your book talks about these. We won't see this that much, but I do want you to know the difference between the three. The gauge pressure is the pressure reading on the gauge. That's what you measure when you measure the pressure in your tires. Though it's a little misleading because, well, if you have a flat tire, then you say, I got no pressure in this tire. But that's not really true, because if you have a flat tire, you still have air pressure in your tire. You still have a full atmosphere, a full 100,000 newtons per square meter inside of your tire. So what your pressure gauge does is it compares the pressure inside your tire to the pressure that's outside the tire. And your gauge pressure is just the difference in those. So it's the difference in the atmospheric pressure and the pressure in the tire. For example, if you're doing tire pressure. Atmospheric pressure is the pressure due to the atmosphere. And then the absolute pressure is the sum of your gauge pressure and the atmospheric pressure. So your book talks about this, I think probably more in depth than I would go, but I want you to know the difference in them. Atmospheric pressure is just sort of what we feel around here. Gauge pressure is that extra pressure that you have inside of a vessel, like a tire, or if you have some pressure, some gas contained in a container. And then the absolute pressure is just the sum of those two. Next time a friend of yours has a flat tire, tell them, say, it's not really no pressure inside of your tire, that you really have a full atmosphere of pressure in your tires. And see what they say. Okay? Huh? All right, so the third source of pressure is the interaction of molecules. So if you have gas inside of a container and you have a certain temperature, then there will be a certain pressure of that. You've seen this before. I know that you have. The ideal gas law. That's right. The ideal gas law describes this pressure. Consider a container of gas. This only applies for gases. So before we were talking about gases and liquids, all fluids. But this only applies to gases. When I say a container, what you should think in that is that a container has a certain volume. And if I have a certain container, then the volume's not going to change. Because you know, gases, unlike liquids, will fill the container. Whatever volume is of the container, it will fill out that container. Right, that's the difference between a liquid and a gas. Gases are also compressible, yes.
So that's the definition of
Not exactly. Compressible just means that, you know, I can take a gas and I can take that same amount of gas and put it into a smaller space. I can compress it. But you can't do that with liquids. You know, you try to take a liquid and compress it down into a smaller space, that doesn't work. Right, that's why our hydraulic systems work, actually, because liquids are incompressible. By the way, do you know why we use oil in hydraulic systems? Why do we use oil in hydraulic systems? Is it more incompressible than other liquids? Like, is water incompressible? Yeah, it isn't. Water is incompressible. I cannot take water and put it into a smaller container. Force it into a smaller container. So why would I? It seems like I should use water in hydraulic system because it's cheaper. What's that? The viscosity?
Yeah, the temperature.
Yeah. Right, yeah, the temperature affects the viscosity. But I think the primary reason that we
Just
use
to keep it oiled, so it doesn't.
keep it
rot.
oiled, right? Keep it from rusting. But water is incompressible. All right. So consider a container of gas. If you add gas, the pressure increases. If you raise the temperature, the pressure increases too. And that's the ideal gas law. PV is equal to N times R times T. P is the pressure, V is the volume, N is the amount of gas. As the number of moles. But we don't need to worry about moles. It's just how much gas do you have? How many particles of gas do you have? R is just a constant. In fact, we can just sort of forget about it for now. We're not even going to worry about R. But we're worried about P, V, N, and T. So what I just said in words is that if I add gas, the pressure increases. That means that if I make N go up, then P also goes up.
What's the middle one?
R, yeah. It's a constant. It's the gas constant.
So
And
then, for on the quiz, on number 9, where it says you increase the pressure of a gas but keep its volume constant, what happens to the temperature?
Yeah, we'll get to that.
Oh, okay.
So if I increase the temperature, if I make T go up, then that means that the pressure goes up. Or, also, if I make the pressure go up, like I have a container of gas and I keep the volume constant, but I increase the pressure, then that means that the temperature will go up. Okay? So we have these relationships between these variables in this equation. Boyle's law, in fact, the ideal gas law is really the combination of two separate laws, Boyle's law and Charles' law. Boyle's law is a special case, or not really a special case, but just sort of a... Huh? What's that? I'm sorry. Say it again.
Avogadro's law.
Avogadro. Avogadro. So Boyle's law is a special case. If N and T are constant, then PV is equal to a constant value. So if I have P and V, and these are constant, what that means is that if one of them goes up, then the other one goes down. And that's the application behind breathing. You guys ever breathe? Yeah, try it for me right now. Take a big deep breath. Brandon, take a big deep breath. Are you breathing? What happens when you breathe? You ever thought about this?
Yes.
Maybe your lungs are muscles, or maybe your lungs just change size. Are your lungs muscles? No, you took your lungs out of your body, they have no muscle at all. They're just sort of bags that sit inside of your body. What do you do when you breathe?
Increase the amount of gas.
Your diaphragm moves down, which increases the pressure.
It doesn't really increase the pressure. I mean, it does sort of, but really what's happening is, and when you breathe, you change the size of your chest cavity. And that's physically what you're doing. When I breathe, I make my chest cavity big or smaller. Yeah, so if I make my chest cavity bigger, that means that the volume is going up. And what happens to the pressure inside of my lungs if the volume increases?
Stays the same.
No.
Oh, the pressure decreases.
Right. So if the volume increases, when you inhale, Sarah, I'll allow you to go take this if you want. Or you can take this. Okay. Give me just a moment, okay? Hey guys, sorry about that. So what was I saying? When you inhale, PV, remember it's constant. When I inhale, what is that? Is my chest cavity get bigger or smaller? Oh, it gets bigger. So V goes up. That means P goes down. That the pressure in your lungs decreases. And then what happens then? Well, all of a sudden I have a really low pressure inside of my lungs. I have a high pressure outside, and air goes into you. It's not you doing it, right? It's the atmospheric pressure is forcing the air down into your lungs. You're just creating a slightly lower pressure by opening up that cavity, that chest cavity. And then when I exhale, what do? I do the opposite. I make that volume smaller. I make my chest cavity smaller, and then that causes a high pressure inside of my lungs, and that air is forced out. You didn't know that, did you? Did you know that?
That's different air that you're forcing out. It's not the same.
Well, it's been processed. Yes. All right. The oxygen. It's been changed a little bit, but yeah. All right. Ideal gas law. Let's try a little experiment. This is kind of cool. What's that?
You're not gonna put the exhale part.
You want to put the exhale? Yeah. So when you exhale, I have P and V. When I exhale, V decreases, and that means the pressure increases. Pressure goes up, so air is forced out of lungs. You didn't know that Boyle's law governed the way that you breathe, did you? Huh? So look, what I have here is a little island. What we're going to do is I'm going to light the matches. Seriously. Y'all want to come up? Caitlin, Blade, Trisha, Dashika? Y'all want to come up? So y'all can see. Y'all want to come closer? Because you can't see back there. I know you can't. Can y'all see? Brandon, you can see? Alan? See? Caitlin? Can y'all see? Because you have to watch. I'll turn the lights on. I'm going to light the matches. Then I'm going to take this little votive candle glass, and I'm going to put it on top of the candle. What's going to happen on top of the matches? What's going to happen to the gas inside of the cup when I drop it onto the matches? Oh, for goodness sake. What's going to happen to the air inside of the cup?
They're going to burn out.
Okay, let's forget about that. It's going to burn. So that means the temperature is going to do what? All right, so the temperature inside of the cup is going to increase. And then what's that going to do? According to the ideal gas law, PV equals nRT. If the temperature goes up, then what's going to happen? The pressure is going to go up. So all of a sudden I'm going to have a high pressure gas inside of this. It's going to be higher than the pressure outside. So what that's going to do?
It's going to float.
It's going to force water out.
It's going to force water out. So I'll put it in after I light it. And you won't be able to see it because it happens really quickly. But it's going to force water out from underneath the sides of the cup. But then, what's going to happen to the matches? They're going to go out. And then, what's going to happen to the gas inside of the cup?
It's gonna explode.
It's going to explode, yeah.
Oh, really?
No. It's going to cool down really quickly, right? It's going to cool off?
And there'll be
Well,
less
yeah,
gas
there's
because of
no-
the chemical reaction.
Right. When the fire goes away, then the temperature will decrease, which will cause the pressure to do what? Decrease.
So then the water's
The water will come back in. All right? You want to see? Y'all, come on. Just stand up and come on. Come on. Come on. Hey. But you can't really see unless you're watching. She's awesome. Isn't she? Come on. Come on. Stand up and like walk up to the front of the compressor.
I'm gonna stand right here for safety hazard.
My eyebrows.
You might not want to sit right there. Like,
Just for reference, the fire reasons. Just.
no, you're fine. It's not gonna happen. You all ready? Are you excited?
Yes.
Watch, because it happens pretty quickly, okay? Oh, did you see? Look! Look at the water!
It's filled with water.
filmed it and did slow-mo.
Look! Can you see where the water is?
Is it empty at the glass?
Yeah, it's all the way up here.
What in the world?
What in the world? Yeah.
Isn't that like the opposite of what you explained?
No.
No?
No. It's exactly because they got that low pressure inside of there.
Isn't that Boyle
Sucks up
saw
all
in
the
NASA?
water.
Sucked it up the water.
All that atmospheric pressure is pushing down.
All that atmospheric pressure. Look, it's like a barometer, sort of. Except we don't have a perfect vacuum. If we had a perfect vacuum, it would be 10 meters tall. Isn't that cool?
Yes.
Aren't you glad you came up here? Okay. All right, I'll go back here. All right, pressure in solids. So solids can also experience pressure. We talked about this later or earlier, but you know, pressure is force over area. So if I have a 110-pound lady in high heels, I have 110 pounds over. Huh?
That was interesting.
It was interesting. This thing.
Oh, what you're saying right now.
Oh, it's in the book.
110 pound
This example is in the
Oh,
book.
yeah.
With different amounts.
Yeah, I forget what the area of the high heels were, but it's a small area, like maybe, I don't know,
Yeah, I think it's
0.5 square inches. Then the force of that, the force on the tip of the high heel is 220 pounds. Isn't that crazy? Thank you, Sarah. You missed it, man. Sorry. But if I have a 200-pound guy on, I don't know, like what's like 100 square inches of his feet probably, then that's going to be just a couple pounds of force, a couple pounds per square inch. I forget what it was in the book. But it's a big difference between the pressure. Now we're looking at the pressure here. This is 200 pounds per square inch. Just this idea that pressure is force over area. So if I make my area really small, if I make my area really small,
300 pounds.
hurt? It hurt? A little bit. Right? Because the area is so much smaller, I increase my pressure. What was that, Kate? What was the
300 pounds.
He was 300 pounds?
Yeah.
What was the area of his feet?
100 square inches.
100 square inches. Okay. 300 pounds.
I know. That's
big
why
guy.
it's so interesting.
All right.
He was open to atmospheres.
So pressure in solids causes stress. Where'd my balloon go? There it is. So imagine this is a solid. It's not really. But if I apply a pressure, then it causes a stress. All right, right? It causes the object to deform in some way. The stress causes a strain. I'm sorry, I misspoke. Let me these mixed up. The stress is the pressure. Strain is the response to that pressure. Usually that's going to be a deformation or a break. If you exceed the elastic limit of a material, like in your bone, they have an elastic limit. We'll talk about that in the next section. Then that material will break. Okay, so stress is the pressure. If I apply a pressure to the balloon, then I apply a stress. And then the strain is the amount of deformation. So the strain here is how much the balloon is shaking. Okay, the stress causes the strain. Stress causes the strain. The stress is the pressure, and then the strain is how much it changes.
So if you see, so in this case, is the elastic limit the strain?
The elastic limit is the maximum amount of strain that the object can manage, so without actually breaking.
So is that kind of like why you get stretch marks?
Huh?
Is that like why you get stretch marks?
Yeah.
Like is that like a
Sort of related, I
kind of
guess.
like a
I don't know.
deformation of-
It is a deformation because you're stretching out,
Yeah.
your skin, basically. When you're pregnant, if you're pregnant, I've never been pregnant, obviously. But when you're pregnant, you're a baby inside of you, and so it stretches out that skin. But yeah, I guess, somewhere that the stretch mark is the strain. Yeah.
Alright, so have you ever seen like someone fill up
No, what?
a balloon with water
Mm-hmm.
and then hold the flame under it?
A flame? Okay, no, I've never seen that.
Well, it does it first. How would that be?
I don't know. No idea. I don't know.
Let's Google it.
And
I'm not
the
gonna-
water
I can Google
absorb
it.
a lot of that energy.
Let's do a couple of these. We're not going to do them all. What'd you say, Steven?
So that imagine the water's absorbing a lot of that energy.
That's probably it. The water's absorbing the energy instead of the balloon. Let's try the one on the left. When you exhale, your chest gets wet. And this causes a wet pressure when you exhale. You can use your lungs as a prop if you want. It's not cheap. I'm not going to say at the exam. Okay. No lungs. All right, let's stop at 45, and then you can go to the one just below there. Okay, C is right. Your chest cavity gets smaller, and so the pressure goes up. Remember PV. If one goes up, the other goes down. So C is right. As one descends to greater depths in a liquid, what happens to the pressure? Does the pressure remain the same? Increase, decrease, what? What? Right here. All right, so a few more seconds, say 25. All right, A is right, the pressure increases. Just like in the video, right? With the bottle going down 70 feet or whatever. Now, what do you do if you're attacked by a gang of clowns? Go for the juggler. All right, let's try it. Tell me which of these pressures, what's the relationship between P1 and P2? This is like a barometer. It's very similar to a barometer. It's actually called a manometer. The only difference between this and a barometer is that this part is open. Actually, no, this part is not, actually. Anyway, what is the difference between the pressure P1 and P2? Just a hint, take a look at the height of the column, right? The height of the column will tell you how the pressures are related. Is P1 smaller than P2? Is it bigger than P2? Is it equal? Or is P1 equal to 0? Is it a vacuum? I'll finish that. I'm going to go ahead and give you the answers for these other two. If T goes up, the pressure increases. So A and B for those other two. Let's stop this at 112. All right, so P1 is bigger than P2. Right, this is the big pressure. Say it's 100 pascals. And then this would be the smaller pressure. Say it's like 98 pascals. And that causes you to have that column. I have something big pushing down on this side, pushing that fluid up into that straw. Yeah.
So is it because it's open?
Because it's open. All right.
So if it wasn't open, P2 would be higher?
I'm sorry.
So if it wasn't open, P2 would be higher?
No, I'm sorry. It's not because it's open. That's not related. I need to ask you a question before you leave, though. So, like, honestly, I'd really love to get a little bit further for this exam. So, it has to be unanimous, but I'm willing to move the exams to Tuesday, and then we would finish up. We'd go on up to page 48. Or we can keep the exam on Thursday. I'm okay with it. Like, the exam's ready to go, and I'll just take some questions out. But you give me your clickers. I want you to click in. And you can either have, I'm sorry, I know it's time to go, but you can either have the exam on Thursday, and we'll just stop at this section, and you won't have any stuff about fluids in motion or flow rate.
I thought it was Tuesday.
Yeah, the exam's on Tuesday.
Right. It can either be Tuesday, and we'll just stop where we are, or we can have it on Thursday, and we can finish up to page 48, which is what your reading quiz is. So tell me A or B, and it has to be unanimous. Tuesday or Thursday. Okay, that's not unanimous. So we'll have it on Tuesday. What's today? Today's Thursday. We'll have it on Tuesday, and it'll stop at this topic. I'll send you the page number in the book, but we're going to stop right here for the test. I'll send you the number of questions and all that. Reading quizzes are similar to an exam. Study those old tests in the book. Bye, you guys. Have a good day.